Welcome back to the deep dive. Today, we're plunging into a really foundational concept in computer science. It's
Mm.
something that pops up all over, puzzles, planning, even problem-solving frameworks.
Yeah, we're talking about the permutation problem.
Exactly.
And we've got some great source material here that really breaks down how you generate all the possible ways you can arrange elements in a set.
Right. Like imagine taking a collection of things,
Right.
maybe books on a shelf or tasks you need to do,
Mhm.
and figuring out every single unique order you could put them in.
That's the core idea, whether it's that workflow sequence you mentioned or trying every combination for a combination lock or just seeing all the ways to line up your coffee mugs.
It all comes back to this. So our mission today in this deep dive is to really get a handle on the concept itself, understand a pretty powerful technique called backtracking, and crucially see the clever ways we deal with the trickier part.
When you have repeating elements.
Yeah, when things aren't all unique. We want to unpack this so it really sticks, so you really get the structure behind it.
Absolutely. It's not just about finding the answer. It's about understanding the structured way you explore all the possibilities, and maybe more importantly, how you avoid doing tons of extra work.
Finding the efficient path.
Exactly. We're going to see the structure, the efficiency, how to solve this thing properly.
Okay, let's start simple then. What exactly is a permutation? Like the basic definition.
Well, at its core, it's just an arrangement. You take all the elements in a set and you put them in a specific order. That order is one permutation.
And the source gives some clear examples.
Yeah, really simple ones to start. If your set is just one element,
But there's only one way to arrange it. One.
right, no choices to make there, but add one more element. Say you have 1, 2.
Okay, now I can have 1, 2 as it is,
Yeah.
or I can swap them. 2, 1.
Exactly. Two possibilities, two permutations.
All right, so it grows. What about 1, 2, 3?
Okay, now it really takes off. For 1, 2, 3, you get, let's see, 1, 2, 3, 1, 3, 2. Then start with 2. 2, 1, 3, 2, 3, 1, and finally start with 3, 3, 1, 2, 3, 2, 1.
Well, okay, that's 6.
6 distinct arrangements. And notice the pattern in the counts. 1 element, 1 permutation. 2 elements, 2 permutations. 3 elements, 6 permutations.
Wait, 1 is 1 factorial, 2 is 2 factorial, 6 is 3 factorial.
You got it. The number of permutations of n distinct elements is n factorial.
Ah, okay, so the goal of the problem is usually to find all of those n arrangements for whatever input you're given, like an array or maybe a string.
Precisely. And the source material pretty much immediately connects this whole idea of generating permutations to a technique called backtracking.
Okay, backtracking. Let's unpack that connection. How does arranging things link up with backtracking?
Well, think about how you'd actually build one of those permutations, maybe manually. You're making a series of choices, right? One element at a time.
Yeah, for 1, 2, 3, the first choice is which number goes in the first slot, 1 or 2 or 3.
Right. 3 options for step 1. Let's say you pick 1. Now for the second slot, what are your choices?
Well, I use 1, so only 2 and 3 are left. 2 choices.
Exactly. And if you pick 2 next, then for the third slot.
Only 3 is left. Just 1 choice.
So you're building the arrangement piece by piece, step by step, making choices from what's available at each stage.
Okay, I see the sequence of choices. How does backtracking fit in?
Backtracking is essentially a general strategy for exploring exactly these kinds of choice sequences. You try building a solution one step at a time, you make a choice, you move forward, you make another choice.
And if you hit a dead end, or maybe finish one solution.
That's the key. If a path doesn't work out, or maybe you've fully explored everything down that path, like finding a complete permutation, you backtrack.
Meaning you undo your last choice.
Precisely. You step back to the previous decision point and try a different option from there. It's like exploring a maze. You try one path. If it's a dead end, you go back to the last junction and try another corridor.
The source mentions a recursive tree idea.
Yeah, that's a great way to visualize it. Imagine a tree structure. The root is your starting point, like an empty list. Each branch coming out of the root represents picking the first element.
So for 1, 2, 3, 3 main branches from the root. 1 for picking 1, 1 for 2, 1 for 3.
Exactly. And then from the node representing 1, you'd have branches for picking the second element, which would be 2 or 3. You follow these branches down.
Until you reach a node that represents a full permutation, like 1, 2, 3.
Right. Those are the leaf nodes of the tree. Backtracking is just a systematic way of exploring this entire decision tree, making sure you visit every possible path that leads to a valid, complete permutation.
That structure makes a lot of sense. Define the choices, build the state step by step, and if needed, backtrack by undoing the last step. Okay, so let's apply this. The source breaks it down into cases, right? Starting with the easier one.
Yes, case 1, Permutations without duplicate elements. So your input is like 1, 2, 3, or A, B, everything's unique.
And the goal is just find all n permutations.
Correct. So in our backtracking framework, the choices are the elements in that input array. The state is the permutation we're building up, maybe in a temporary list.
And the big rule here is you can only use each original item once in any single permutation. You can't suddenly have 1, 1, 2 if you started with 1, 2, 3.
Exactly. The elements in our current partial state have to correspond to unique instances from the input. So the critical question is, how do we keep track of which original items we've already put into our current path so we don't accidentally use the same one twice?
Sounds like where we need that first optimization the source talks about, or repeated choice pruning.
That's the one. This is the first major efficiency gain. Instead of blindly trying every element from the original list at every step, we need a way to know which ones are already taken for the current path we're exploring.
How do we track that?
The standard way is to use a helper array, usually a Boolean array. Let's call it selected. It's the same size as the input array. Selected I will be true if the element at index A of the original input has already been added to the permutation we're currently constructing.
Okay, so before I even consider adding choice chassis to my current permutation state, I first check selected I, if it's true.
You skip it. You prune that possibility right away for this path. You don't even try to add it because you know it's already in use further up the path.
Got it. That seems like it would cut out a lot of wasted effort.
Oh, massively. The source shows this, like in figure 13-6. Without this check, you might explore nonsensical paths, like trying one, then trying one again. The selected array stops that immediately. It guides the search directly towards valid permutations. Instead of a potential ON complexity, if you were really naive, this pruning helps keep the exploration proportional to the actual number of permutations, ON.
Right. It focuses the search only on valid steps. So walk me through the backtracking logic again with this selected array in mind.
Okay. You have your recursive function. Inside it, you loop through your original choices, from index I equals 0 to n1. For each choice chassis, you first check, is selected T false?
Meaning, is this specific item available for use right now?
Exactly. If it is available, selected I is true, you then perform the attempt step. 1. Mark it as used, set selected I is true. 2. Add it to your current state. Append choice chassis to your partial permutation list. 3. Explore further. Make the recursive call to continue building the rest of the permutation.
And after that, recursive call returns, whether it found a solution deeper down or just finished exploring.
That's when you do the crucial retract or backtrack step. 1. Remove the element. Take choice chassis off the end of your state list. 2. Mark it as available again. Set selected I is false.
That set back to false is key. It undoes the choice for this specific path, allowing choice A to be potentially picked later in a different branch of the search, maybe at a different position.
Precisely. That retraction is what allows the exploration of all valid combinations. You try using choice chassis here, explore all consequences, then undo it so other branches can use choice chassis elsewhere.
Okay, that feels pretty clear for unique elements. Track which specific instances used was selected. But now, the tricky part, what if the input has duplicates? Like the source's example, 1, 1, 2.
Right. This is where things get more interesting. If you just use the selected array method, think about what happens. Let's imagine the input is 1A, 1B, 2, where 1A is the first one and 1B is the second one.
Okay.
The selected array would correctly stop you from making 1A, 1A, 2. Fine. But it would allow you to generate 1A, 1B, 2 down one path.
And then later, maybe starting by picking 1B first, it could generate 1B, 1A2.
Exactly. But if the problem asks for unique permutations based on the values, then 1, 1, 2 is just one result. We've generated a duplicate.
And just generating everything and filtering duplicates afterwards feels inefficient, especially if there are many duplicates.
It is. The source points this out. It's much better if we can prune the search tree before we even generate those duplicate results. We need to stop ourselves from exploring redundant branches.
So we need another kind of pruning. This must be the equal element pruning the source mentions.
That's the one. The goal here is different from selected. With duplicates, we need a way to make sure that for a given step in building the permutation, if we have multiple identical values available as choices, like the 2 1s and 1 1 2, we only start exploring down the path for that value once.
Okay, how is that different? Let's use 1, 1, 2. At the very first step, my choices are the first one, the second one, and 2.
Right. Now, if you choose the first one, you'll go on to explore all permutations starting 1. Let's say you finish all of those and backtrack to this first step. Now, if you then choose the second one,
I'd also go on to explore all permutations starting 1, but those would be exactly the same set of results I found when I started with the first one.
precisely. That second exploration starting with 1 is completely redundant. Equal element pruning aims to prevent that second exploration.
So selected tracks if a specific item instance is already used in the current path. This new pruning needs to track if a value has already been tried as the choice for this specific step.
You nailed it. Selected is about the history of the path. This new check is about the choices being made right now, at this level of recursion, within the loop that tries different next elements.
How do we implement that? How do we remember which values we've already tried at this step?
The common technique described in the source is to use a temporary data structure, typically a hash set, let's call it use value set the step, or maybe just memo, inside the loop of each recursive call. This set is created fresh every time you enter the loop to decide the next element.
Okay, a local set for each decision point. What do we check?
Before you decide to proceed with choice chassis, you check two things. One, is this specific instance available? Check .selectedI, same as before. Two, have we already tried using this value choice chassis at this specific step in the permutation building? Check if the value choice chassis is not currently in our local use value set, this step set.
Okay. Both have to be true. The item instance is free, and we haven't already kicked off a search using this value from this exact decision point.
Exactly. If both conditions pass, then you make the attempt. 1. Mark this value as tried for this step. Add choice chassis to the local used value set these step set. 2. Mark this instance as used in the path. Set select dial true. 3. Add the element to the state. Append choice chassis to the partial permutation. 3. Add the element to the state. 4. Recurse to continue building.
And the retract step.
Same as before for the state and selected. Remove choice chassis from the state list. Set selected data false. The crucial part is that the used value set the step set was local to that loop iteration within that recursive call. When the function returns or the loop moves to the next potential choice, that specific set's job is done. A new one might be used if needed deeper in recursion, or the previous level set is still relevant there.
Okay, wait. The local set gets wiped or goes out of scope. So when I backtrack up a level, I can potentially use that value 1 again, just not twice in the same set of choices at the same level.
Exactly. That local scope is critical. It prevents trying the same value multiple times as the immediate next step from a single node in the decision tree. But it doesn't prevent using that value later down a different branch or earlier up the tree.
That makes sense. It's a very targeted pruning for that specific decision moment.
Yeah.
So let's try to contrast them again, like the source does.
Okay. The selected array, that's about repeated choice pruning. It's like a global state for the current path down the recursion tree. It tracks which original item instances are already part of the partial permutation you're building. Its job is to stop you from picking, say, choices 2 if choices 2 is already in your state.
Right. Tracks the specific items used so far down this one path.
Then you have the local used value SAFI step set. That's for equal element pruning. It's local to the for loop inside one recursive call. It tracks which values have already been chosen as the next element branching out from this specific point in the tree. Its job is to stop you from starting a new branch with value X if you just started another branch with value X from the exact same place. This is only needed when your input has duplicate values.
Okay, selected main as instance reuse in path. Use values, value reuse at this specific choice point. Got it. That second one is definitely the key insight for handling duplicates without generating extras. It's elegant, actually.
It really is. It comes from carefully analyzing where the redundancy happens when you have identical inputs.
Okay, efficiency. Let's talk complexity. The source says time complexity is generally ON. The N part is clear. That's how many unique permutations there are, roughly. Where did the extra factor of N come from?
Good question. So you generate N distinct permutations in the unique case, or fewer with duplicates, but N is the upper bound. Each time your recursion hits the base case, meaning you've built a full permutation of length N, you usually need to record that result.
Like adding it to a list of all permutations found.
Right, and creating a copy of that permutation, which has N elements, to add to your results list typically takes ON time, since you do this ON operation for each of the ON permutations you find.
ON times ON gives ON. Makes sense. The cost per solution times the number of solutions.
Exactly. The backtracking with pruning ensures we're not doing vastly more work than necessary to find those solutions, but we still have to actually build and store them.
Okay, time complexity clear. What about space? The source mentions ON2. Where does that come from?
All right, let's break down the space usage. First, the recursion itself. The maximum depth your recursive calls will go is n, right? Because that's the length of a full permutation. So the call stack uses ON space.
Okay, ON for the stack depth.
Then we have the selected array. That's always size n, so it's another ON space.
ON plus ON is still ON. Where's the N2?
It comes from those local use values at the step sets we use for duplicate handling. Remember, a new one of these sets is potentially created inside the loop at each level of the recursion.
Right, the temporary scratch pad for each decision point.
Yeah. While any single set might hold at most n values, if all elements were unique, which is unlikely if we're using this, the issue is that as you go deeper into recursion, you have multiple active recursive calls on the stack. Each of those calls might have its own local used value set existing simultaneously.
Ah, so if the recursion goes n levels deep, and at each level we might allocate a set that could, in the worst theoretical case, grow towards size n, the total space used by all these active local sets across the stack depth could sum up to ONN or ON2.
That's the idea. The recursion depth contributes 1n, and the potential size of the state being maintained at each level, including these local sets, contributes the other n. It's the cumulative effect across the stack.
Okay, that clarifies the ON2 space. It's not immediately obvious, but thinking about the state held at each level of the recursion stack makes sense.
Yeah, analyzing space complexity with recursion, especially with local state being created, requires looking at the total footprint across the maximum call depth.
Right. So we've gone from the basic definition, framed it as choices and backtracking, used selected for unique items, added the clever local used values set for duplicates, compared those pruning methods, and looked at time and space complexity. That feels like a pretty thorough deep dive.
I think so too. And like we hinted at earlier, this isn't just some abstract CS exercise. Understanding permutations and backtracking, it actually pops up.
Where might someone listening actually encounter these ideas, maybe without realizing it?
Well, anytime you need to systematically explore all possible orderings, complex scheduling maybe, figuring out the best order for tasks. Route planning, while much more complex in reality with maps and costs, has a core element of exploring sequences of places.
Generating test cases for software, trying all sequences of inputs.
Definitely. Puzzle solving, like Rubik's Cubes or certain types of logic puzzles, can often be modeled as searching through sequences of moves. Backtracking is key there. Even some aspects of cryptography involve permutations.
And the techniques themselves, thinking recursively, using backtracking, and especially finding ways to prune the search, those seem like really valuable general problem-solving tools.
Hugely valuable. The backtracking framework gives you a structured way to attack any problem where you can think of the solution as being built through a series of choices. And the pruning part, that's where the efficiency comes from. Learning to spot repeated choices or equal choices that lead to redundant work is fundamental to algorithm design.
It's about not just finding an answer, but finding it smartly, avoiding wasted effort.
Exactly. Don't just explore blindly. Prune the paths, won't lead anywhere new or valid.
Like knowing which doors in the maze are definitely locked or lead back where you started.
Perfect analogy. You want to avoid trying those doors at all.
Okay, so we've journeyed through this permutation problem, defined it, saw how backtracking naturally fits, learned about the selected array for basic pruning, and then the more subtle used values set for handling duplicates efficiently.
Right. We saw how viewing it as choices in a tree, managed with recursion, lets us cover all the bases, and how selected stops reusing specific items in a path, while the local used value stops redundant exploration of identical values at each specific choice point.
That distinction really is key, isn't it? Instance reuse versus value reuse at a specific step. Mastering that seems crucial for getting the duplicate case right.
It absolutely is. It shows how you need to tailor your pruning strategy to the specific source of redundancy in the problem you're facing.
So a takeaway for you listening: the next time you face a problem that feels like finding all possible arrangements or sequences or combinations, or maybe even a problem you can rephrase that way, try thinking about it in terms of backtracking.
Can you break it down into a sequence of choices? Can you systematically explore those choices using recursion?
And crucially, are there shortcuts? Can you prune the search? Can you identify choices that are immediately invalid, or choices that will just lead you down a path identical to one you've already explored or will explore?
That thinking about the structure of the search and where the waste is, that's often the difference between an algorithm that just works in theory and one that actually finishes in your lifetime.
A great final thought. How to search smartly. Something to chew on next time you're faced with exploring a world of possibilities.